So, welcome back, everyone. Just before we start, wait. So we start now with the second lecture by Leah. She's really eager to get into the blackboard or the whiteboard. And just as your announcement, tomorrow the question section, so Leah will also lead the question sections. So I think she'll have some exercises and she has some really nice ideas of what to do in this question section. So without further delay, Leah, please take.
Hello, everybody. How are we this morning or afternoon? Yeah, it's still morning for you, right? It's a little bit earlier for me. Yay! So I just also wanted to mention that these people that I see are joining via Google Meet. If they have any questions, feel free to use the chat line and ask. So not just the live audience, but those of you that are joining virtually are also encouraged to ask questions if you want. Okay, so let's review what we talked about yesterday. So we met the Grothendieck group. We computed in one or two very simple cases. We will do more examples probably tomorrow. And then we started going towards these graph algebras. We met one of them called path algebra. And just to remind you, path algebra can be defined using these two axioms called V and E1, right? So today we are going to go further with these axioms. And we are really going, so today it's all about understanding why the axioms look the way they do for path algebra and for graph sister algebra. Because you see, I don't want to say it's a default, but it often happens that you are just presented 5 axioms, go, without kind of, going a little bit behind why does something look the way it does? Why do we need 5? Why are not we happy with 3? So this is where I want to go today. Eventually, we are going to get what a graph sister algebra is, what Leavitt path algebra is. We're going to do a bunch of examples, but at least first half an hour is going to be about why we need more axioms and why we need exactly the axioms as they are. So let's first talk about why we are not happy with path algebra alone. Path algebra is too free. In other words, there are just this minimum requirements that hold for you to know where one path ends and where the other begins. And pretty much there is nothing else. So, in a way, that algebra is too big. You want to cut it with more relations. So one thing that you would also want, besides this being too free and too big, is to have something called an involution. So you see, when you say C-star algebra, not necessarily graph related, just any C-star algebra, we see this star right there on top of C, right? So the star comes from involution, and somehow you would want to be able to involute your basis elements. In other words, you want to be able to figure out what is kind of V star and what is E star for an edge. So that's why there are more axioms, and that will all feature in one way or the other these stars. So before we go to the axioms themselves, let me tell you what is a star ring, just so that we understand all these stars that are going to come later on. So an involutive ring is simply a ring with this unary operation star. unary means that it maps R to R on 1. That's the unary part of it. And you want it to be additive. What does that mean? That means that x plus y star is x star plus y star. And you want it to be such that the familiar operation for transpose of matrices holds. So for example, if your x and y happen to be matrices, and if your star is transpose, it's not going to be x transpose times y transpose. It's going to be y transpose times x transpose. So, so that's your axiom how star relates to times. And then you want one last one that is going to pretty much tell you that in case of matrix is a transpose of a transpose is again your original matrix. So this is a star ring with such an operation. Let's talk about a few quick examples before we go any further. So one of them I already mentioned. So if you have matrices over, let's say n by n, over a ring R, then the transpose is a star for you. Let's talk about another famous one, very famous one. If R is complex numbers, we do have a famous involution out there, which is complex conjugate, right? So your x plus iy star is x minus iy, right? Very, very important one for like C-star algebras. And then let's do another kind of, in a way, trivial example. So if R is commutative, then you can take star to be identity, and that works certainly. So, you know, if this is doing nothing and R is commutative, then xy is indeed equal to yx. This certainly holds if star is doing nothing, right? And this certainly holds. And then the last one is maybe the most relevant to us, the example most relevant to us. Not because of graph algebras, but certainly because it's most general. So if your graph algebra happens to be representable by matrix algebra of some sort, like the one that we have seen yesterday, then this example is really good for you. So imagine that R is a ring with some involution star. So R is a star ring. This gives you a way how you can extend this involution to matrices over R. So I want to define a star on a matrix. And what do you do with a matrix that has entries A, I, J, for example? How you star such a matrix? You take the transpose, and so that would be going from Aij to Aji. That's what taking transpose means. And then you star with this star from R each individual entry. Okay, so let's add those stars to our path algebra for a start. We are good with these examples so far. Everything I say makes sense. Please interrupt me. If you have a question, just stop me. Don't wait for me to ask. Okay, so you were given a graph E. It doesn't have any stars right now, right? It just has paths and vertices and edges. That's it. So you define something called extended graph. And I will denote it with E hat, which consists of vertices, edges of the original graph. So if you have edge E with source and range, that's all there. And then you add edges going back. So you add something called a ghost edge. For every edge E, you define a ghost edge called E star, and you're thinking it looks like this. So the vertices of E star are the same. I will say vertices are those of E. So E0 of this is E0 of that. I didn't add anything there. Edges are the original ones, E from E1. And these ghost edges for every E, you also have a way to go back. So I will denote them, I will graph them in different color, just so that we keep track of what was originally there and what is added because we need these stars. So now we have ghost edges as well, right? And then to make the concatenation of ghost paths natural, you are adding an axiom called E2. So E1, if you remember, deals with edges, and E2 now is going to deal with ghost edges, and it's pretty much going to say the same thing as E1. Except that it is for ghost edges. And since we may forget what is E1, let me write it down here, just so you see that it is the same exact thing. So what was E1 saying? Source of E times E, source of E times E is E, and E times range of E is also E. So how is this axiom, this new one that I'm adding for ghost edges, how is it going to look like? I want to say source of E star times E star is E star. But what is source of E star? Source of E star is range of E. So I will say range of E times E star is E star. And the second half of the axiom is saying that E star times range of E star should be E star. So E star times range of E star. What is range of E star? It is source of E. So you see, now you have something like path algebra, but not over the original graph, but over the extended graph, right? So let's see what kind of products in this, with these additions, what kind of products we have. So let's go back to our maybe favorite graph for this course, this short course, because we keep going back to it. So let's let this be E and F. Let this be like U, V, and W. So let's talk about what kind of products we have here in a path algebra over this extended graph. Let me, for time being, also write down these ghost edges, right? So F star would look like this, and E star would look like that. And these products that are easy to compute, let me call them obvious. So some of the products are, for example, if I have F star times U, what would that be? F star doesn't end at U, U is all the way over there, so that would be 0, right? If I have F star followed with E star, F star followed with E star, that makes sense. That is the element called F star E star, right? It's not 0. This is one of my basis elements of that path algebra. And then you see there are more products like this that are kind of obvious. We can easily compute them. But what is not obvious? So for these, I kind of think they are like easy to tell what they are. So I call them obvious. So what is not so obvious? Like what would be E star times E? So you see E star and then followed by E. That's kind of composable because this one ends where that one begins. So is it maybe equal to something already on this picture? Maybe it's equal to U, or maybe V, I don't know. Or maybe it's equal, or maybe it is a new basis element not equal to anything, right? So the question here is this equal to something on this picture? Or is it maybe not equal? Is it maybe just, you know, the new basis element? So this is not obvious. And then same thing for F. And then same thing for, like, you see, you can compose here E. Well, here you cannot compose F star and E, but in general, you know, if you have first star of something and then some other edge, what is that equal to? And here you can also say what is E star here and what is F star here. So all these products right now, we are not exactly sure what they are. So that's why we need more axioms, so that we specify for each graph algebra that we are about to make what things like these are. So just to motivate you a little bit for the answers to these questions, we need just a tiny bit more background on star rings. So we are just going to go back to star rings in general, and we are just going to talk about something called a projection and something called a partial isometry. And after that, I promise axioms are coming very, very soon. So what is a projection? So I have a star ring R. So R has good old plus and times, and now it has this operation star, right? So a projection is an idempotent. What does that mean? Idempotent is, let's call projection P. So that means that P times P is P, right? That is what idempotent means. And it is self-adjoint. What does that mean? That means that P star is equal to P. So you see, in the world of star rings, idempotents are nice, but these projections, they are even nicer. So if you are working in star algebra, C-star algebra world, you will almost never see an idempotent. Like if you are having only a ring on your hand and you're looking at Grothendieck group or, you know, direct summons, then these idempotents are really, really important. But if your ring has a natural star attached to it, like C-star algebras do, then projections take over the role of idempotents. So in our example with graphs, our main example are the vertices. Because remember that we didn't add any star of vertices. That means that we will want V star to be equal to V. If I'm able to star everything in my algebra, I want to know how to star vertices as well, right? So, so this will hold. And if you remember the first axiom, the V axiom, tells you that V times V is V. So that's why vertices are going to be projections. And what is a partial isometry? Let's say that this is example. And what is a partial isometry? It is any element X such that X times X star times X is equal to X. Okay, so why why this definition, where this comes from, why do I care about such an element? Because if X is a partial isometry, then I'm claiming that both this and that are projections. Let's see that this is not so hard to see. So let's say that P is equal to X star and Q is equal to X star X, right? I want to convince you that these two things are idempotent and self-adjoint. So let's see what is PP. So this is X star, X star. And we know that X is a partial isometry, so this is X. So this is X star. And what is X star? It is P. And it is self-idempotent because P star is X star star. And how do we star a product? We switch it around and then we star each entry. And what is X star star? That's just X. So there you get your P back, right? And you can convince yourself that this other part here is also a projection, right? So you see here we have something that I will, this identity here that now I will write in terms of P and Q. So remember, we call this first part P. So this is telling you that Px is X. And we call this second part Q. So this is telling me that Q is also X. So take a look at this identity here. Does it remind you of something? Something that we have seen maybe about 10 minutes ago. This identity here. Does it remind you of one of the axioms here? The one that looks like E is equal to E range of E and source of E is E, right? So you see, because of this kind of, analogy here, you want your partial isometries in the graph algebra to be edges. So what we want is we want edges to be partial isometries. And I'm not saying that this will that source of E is always going to be exactly equal to X star, but at least this gives us some type of analogy. Let me put like quotations, source and range. So maybe not exactly source and range, but something to do with source and range is going to be there. So what does that mean? That we want E times E star E to be equal to E, right? That is going to give us that edges are partial isometries. And actually, in the world of star rings, this is called source and range. In actually the reverse nomenclature than in the graph algebra world. So if you're reading a book only on star rings, there is the reference that this is actually range and this is source. For graphs, it's the other way around. But it's good to keep in mind at least this like the relation between this definition of partial isometry and these roles of these two projections and the source and ranges of the graph. So to achieve this goal, we are going to add another axiom that is called Ck1. Ck stands for Kunz-Krieger. And Ck number 1 means that there will be also Ck number 2, not more than, well, there will be Ck3 for graph sister algebras, but not more than that. So there are some Ck axioms. And this first one is telling you that E star E is going to be range of E. Okay, so first little exercise for you is I want you to think, it's very, very short argument, super short. But you see, if you think about things on your own and not just hear it from myself, that is really going to help you understand this material better. So now, right now, try to scribble on the piece of paper, why is this going to give me that E, that if this is range of E, how does this give me that, that this product is going to be E? And keep in mind of that axioms that are already available to us. So you look E, R of E, so that will indeed give me E. So you see, this is why, that's why we add this axiom, because that thing alone is going to give me that edges are partial isometries. I also want edges to be orthogonal partial isometries. So there is another part of this thing. So let's also write what else we want. We have seen this word before. Let's try to remember from yesterday's story in which sense we have seen that. We have seen it yesterday when we wanted these vertices that are different to multiply to 0, and then we said that they are orthogonal. So, so in that same sense, right? So we want these edges to be such that not really that they are themselves orthogonal partial isometries, that but such that we have orthogonal projections in E star E and F F star. When E and F are different edges, we want E star and F star to be orthogonal projections, right? And in a way, that will imply that E star and F are orthogonal partial isometries. Again, orthogonal in this sense that that product is 0 if they are different, right? So the part that we add, right? So we want this, and then we want something else, and then something else is going to give us exactly this. So so we are adding that E star F is equal to 0 when E and F are different edges. So again, a little brain teaser for you is the following. If I assume that E star F is equal to 0 when E is not equal to F, try to show that that is equivalent, that E star F star is equal to 0 when E is not equal to F. One direction is very easy to see, right? So if this heart of this product is equal to 0, then everything will be 0. And you will just need a little bit of another axiom to show the other part. And I really want you to try to do these little exercises that I'm telling you, because then you're getting more familiar with these axioms. You are gaining working operational expertise. When you are just solving these exercises, you feel more confident, and then you understand things better. And I probably don't even need to tell you that, because that's how you pretty much get to sit in this room, by doing the little exercises when you were sitting in your classes, undergraduate or graduate, doesn't matter. Okay, so now we have the whole axiom in front of us. So one more to go, the last axiom. Let's talk about Ck2 axiom. Let me erase Ck1. So Ck1 is good because it specifies what one of these non-obvious products is. So I know that E star E is range of E, right? Ck2 is going to give me the other version of this order here. The other, if it's not E star followed by E, but if it is E star. And Ck also gives me something very, very precious, right? So it will tell me how many edges vertices emit. So you see, so far, based on the axioms that we have a sense of where one path ends and where the next one begins, if that happens in the same place or if that happens in a little bit different place. You also have in these axioms like encoded about the source and the range and about the ghost path making this nice loop, right? So E star followed by E is going to be range of E. So the Ck2 axiom is about sources, right? And since that Ck2 axiom is going to keep track on how many edges vertices emit, this is going to be a pretty good axiom to have. So this axiom Ck2, since it's going to take into consideration how many things are being emitted from a vertex V, let's specify for what kind of vertices we are going to be interested on. So let's say that V is a vertex that doesn't emit anything, right? So maybe it receives something and it doesn't emit anything. So if V doesn't emit anything, we call it a sink. And we don't care about these vertices right now. So if V is a sink, we don't have anything for anything added for V, right? Okay, another type of case that we are not going to be interested at is vertex that emits infinitely many things. So if V emits infinitely many edges, we are going to call it infinite emitter. And if V is not of this sort, so if V is not a sink, nor infinite emitter, we say it's regular. And that means that V emits finitely many edges. So Ck2 is only for regular vertices. Okay, and what we are saying for these regular vertices is that V is sum of E star for all edges V emits. So you see, this is going to specify what E star is, or at least where it belongs, in what kind of sum it belongs. If E is, so I want to say here, E is edge emitted by V. How can I say that like in a short form? Remember that that the source map tells me what is the source of E. So I want to say V is a source of E, so I will say E is in S inverse of V. And remember what regular means. Regular means exactly that S inverse of V is non-empty and finite. So before my first example, let me now give you, this is a great moment in these 2 days. I'm giving you definitions of these graph algebras, because now we know all the axioms. Now we have seen all of the axioms for Leavitt path algebra. And before the examples, and there will be many examples of Leavitt path algebra in the remainder of the class. So before these examples, let me finally give you the definition of Leavitt path algebra. So Leavitt path algebra of E over a field K. People these days, they do Leavitt path algebras over not necessarily fields, over commutative rings. There is millions of generalizations of Leavitt path algebra over like generalized versions of oriented graphs. So we are going to try to keep things simple for time being. Let's not go crazy and overboard with these generalizations. Let's just stick to the field. Let's just stick to the oriented graph. There are still many things that we don't even know about these things, so let alone generalized things. So K is a field, E is a graph. This is Leavitt path algebra. Let's write actually down. So this is Leavitt path algebra of E over K. One of my examples is going to be about Leavitt algebras. So then we are going to see why, you know, this type of algebra has the word Leavitt in it. So this is again free K algebra over, let's write it down. Over pretty much basis of this extended graph. So over E0, E1, and these ghost edges that we added, right? E star when E is in E1. Subject to. And now I will just list all the axioms that we have seen, right? So there's 5 of them total. So one was V, the other one is E1. So this is path algebra axioms, right? And then we have E2 to handle what are the sources and ranges of E star, right? And then we have Ck1 that specifies what is product if F star comes before E. And then we have Ck2 that specifies the products of this sort, E first and then E star second. So in this talk, I'm going to focus, well, not in this one today, but you know, throughout this week, I'm going to focus on Leavitt path algebras. Just not, again, to go overboard with C-star algebras as well, but I'm going to tell you what graph C-star algebras are. So when I say graph algebras, I usually mean Leavitt C-star algebra or graph C-star algebra. And actually, most of the things that we are going to do, this graded version of K0 theory, and these like irreducible representations, what I'm going to talk about in the last day, everything that I'm going to tell you will have its graph C-star algebra version, but we are just going to focus on Leavitt path algebras, again, just not to go overboard with topics. This is going to be, you know, a pretty full course as it is, so let's not go overboard with graph C-star algebras. But I'm going to tell you today what it is, and I'm actually going to talk about why it has become why is it that these things have become so popular. So what is the appeal of graph C-star algebra and what is the appeal of this Leavitt path algebra. Why all of a sudden people start going crazy about these like 5 axioms and so much structure. So for us to understand what is a graph C-star algebra, I'm just going to tell you about one more part of the structure of star rings. So before we go to graph C-star algebra, let's just go for a second to a star ring, and let me give you the one binary relation on projections. So this is like an order. And this is saying that P is less or equal to Q if P is both PQ and QP. So you see, if PQ
Leah?
is equal...
So I see that there is a question in the chat. Do you have access?
Let me try to figure it out. So E star star. Okay, so let's actually go over this. So E star star is going to be E, because remember that one of the requirements in a star ring is that X star star is X. So that's why E star star is going to be E, right? Thank you for your question. And I'm glad that I was able to figure out where the chat line is. So this is the order. Again, when I say order, if you're not sure what that means, please interrupt and ask me. So this means that it's reflective, anti-symmetric, and transitive. A little exercise for you: write down that that is indeed so. Write down that this is indeed all these things that I'm telling you, right? So also try to use your axioms to show that if this consists of more than one term, then every E star is going to be less or equal to that V, and V is that source of E, right? For Leavitt path algebra. And then if you convince yourself of that, so this less or equal again is defined here, right? Try to write down, convince yourself that that's true. Again, use the axioms. Then I can tell you what a C-star algebra is. A graph C-star algebra. So a graph C-star algebra is what they say in C-star algebra world. It is universal C-star algebra. So in our algebra world, that will correspond to free algebra over something, right? So it is universal C-star algebra generated by vertices and edges which are orthogonal projection and edges which are orthogonal partial isometries. Orthogonal. So you see, because I'm requiring that orthogonality, that is going to automatically give me something like V and E1, right? So I don't have to require that to automatically hold. And because C-star algebra automatically comes with star, that will give me actually E2 also, right? So I don't have to require these things additionally. So I need to require the following 3 things. I need to require Ck1. Let's write down. So it's generated on this subject to CK1, CK2. So CK1 and CK2 hold exactly as I told you what they are for Leavitt path algebra, same exact thing. And then we also have CK3, which is telling me that for every E star is less or equal to source of E. So you see, this, if you convince yourself of that, then you will believe that you don't need to require CK3 for Leavitt path algebra, because it will follow from other stuff, right? But here, in C-star algebra world, somehow we have to require it additionally. In my notes, I have 2 exercises for you. Show that pretty much what I also told you about here, right? Show that CK3 calls for Leavitt path algebra. And bottom of page, what is it, 7? I want you to try to show that E1 and E2 called for graph C-star algebra, right? So everything that is missing up there, which is CK3, holds, and everything that we are not requiring here, meaning V and E1 and E2, holds in here, right? Now, before we go to examples, let me just tell you what is the big deal with all of these graph algebras. So chronologically, graph C-star came before Leavitt path algebra for a number of years before. Not too big, like, I don't know, between 5 and 10 years before. So the world of C-star algebras is vast and complicated. C-star algebras are some fancy algebras. They have norm, they have topology, they have this concept of continuity. They have much harder structure than our simple little algebras, right? So people are trying to understand that world, that vast world, so they divide it in pieces. So instead of studying all C-star algebras, they study such and such C-star algebra and finite in some sense, not in the sense that they have finitely many elements, but in some other sense, and then purely infinitely finite, and, you know, one class or the other. So somehow, when people start considering graph C-star algebras, the structure of those is much more simple, because you see they are based on graphs, and a lot of things you can get simply by graphing that little graph and playing with vertices and edges. And it turns out that in each of these classes of C-star algebras sits a very nice representative, which is a graph C-star algebras. So let me call it C-star related to some graph E, C-star related to some graph E. So in every of these categories of the whole thing, we have very nice representatives, right? And that's why graph C-star algebras became so popular. And then people came up with Leavitt path algebra. And if you're looking at Leavitt path algebra over complex numbers, and if you complete it to a norm with respect to the norm, so this has some pre-norm structure that we don't need to go into the details today, but, you know, it is useful to think that this sits inside of that, and somehow it's dense, right? Dense, it's a big chunk of C-star algebra, and then when you complete this Leavitt path algebra with respect to that missing norm, then somehow you end up in C-star algebra. So you see, this makes your whole world even simpler, because if you want to study these nice representatives, it is kind of enough to study their Leavitt path algebras base. And that's why Leavitt path algebras are so, like, I wouldn't say super widely spread, but certainly widely spread today. So now that we maybe hopefully understand a little bit more about why things are considered here, let's go to my favorite part of today's lecture, which are examples. Don't you love when, you know, when we are done with definitions and then we can just play with some down-to-earth graphs? So let's go first and foremost to this star of the show, if you want, of today and yesterday. So U, V, W are your vertices, right? And E and F are your edges. I want you to think. After a while, you will not even graph these ghost edges. You will kind of just know that they're there. But for the first time, let me do them, and let me do them in different color. So let's see what kind of products we have here of those that were not so obvious before, right? So E star E is range of E. F star F is range of F. So these are pretty much, these are all coming from CK1. I know that F star E and E star F are equal to 0. In this particular graph, these things, we don't need any axiom to conclude that these are 0, right? They are kind of obvious that they are 0 from the graph. But sometimes you see F star may be such that it ends where E star begins. So this is not obvious that such a product would be 0. So pretty much these come from CK1. Let's write down what comes from CK2. So E star. Here, let's first look at U, right? U emits only one edge. So E star is U because U doesn't emit anything else, so that you have plus something else, right? And F star is V for the same reason, because V emits only F. So you see, for this nice graph, everything is kind of nice because E star ends up being actually a vertex, and so does F star. And this is pretty much your algebra. And just to give you also something else, a nice way to think of this as matrices. So I will just remind you that yesterday we computed path algebra of this graph, and it was isomorphic to these matrices that are upper triangular. So I may have something here and everything below is 0, right? And let me remind you how we used to write this isomorphism. So this was UVW, this is EF, and this is EF. Okay, so now what I'm claiming here is that Leavitt path algebra of this graph is isomorphic to the entire 3x3 matrices, algebra of entire 3x3 matrices. And you can convince yourself of that if I append this map from yesterday with E star here, F star here, and so I want EF star, which is F star E star down here. So again, what do I mean by this? That means that all these basis elements that I have, right? I have 3 vertices and 2 edges and 1 EF, right? And what else do I have now? I have 2 ghost edges, and I have 1 EF star, which is F star E star. So I have 9 of them together. That they exactly correspond to these matrix, standard matrix units. So for example, E star, I will map to E, what is it? Second row, first entry, right? And for example, like F star, I would map to E, what is this? Third row, second entry, right? So again, try to convince yourself of that, and then you will have just that this nice graph has this nice representation. Are we buying this?
Sorry, Leo. Someone's not buying it.
Just a quick question. Why from CK2 it does not follow that V is the sum of F star and E star E.
Because in here, your sum consists of only one element, right? So the axiom is saying that V is E star, where E is in the set S inverse of V, right? So what is here set S inverse of V? S inverse of V here is the set of all edges that V emits, right? And that set is just F and only F, you see? So that's why your sum has just one term here, right? So Ck2 for V is saying that it is F star. There is nothing else that V emits. Actually, my second example is going to be if I maybe change this, so then I have that V emits two things, not just one. That was going to be my second example here. So
sorry, when you complete S minus 1 of V, you are not considering the ghost edges. So E star does not.
That's right. That's right. That's right. So this range and source maps for, I'm still keeping for the original ones. Yes, that's a very good point. I'm so glad that you asked that, because you see my experience with question. If one person thinks something, that means that at least 3 other people are thinking the same thing and maybe are, you know, hesitant to ask. So thank you very much.
Thanks to you.
Very good question. Okay, so let me change the this a bit, and let's see what our Ck1 and Ck2 are for this graph here. And actually, let me not even graph the ghost edges anymore. So here we have that U and W are sinks, right? So there is no relations for those, right? And your Ck2 applies only to V. Right? And now V actually emits 2 things, right? So your V emits both E and F. So your source inverse of V consists of both E and F, right? And then your V is E star plus F star. So you see, somehow the number of terms in that axiom Ck2 tell you about how many edges you have emitted. So I see that we are almost out of time. So let me just, before we part for today, so I don't think that we will see what Leavitt path algebra is, but let me at least tell you about Laurent polynomials and no exit graphs. So let me, pretty much now I'm on page, like bottom of page 8, if you're following the notes. So let's do example 2, or 3, if we count this other graph as an example. So far we have seen something that kind of is like a matrix algebra, right? We will see in a bit later today, maybe, that this other graph that we just did, E and F, can also be represented as matrices, actually sum of 2 matrix algebras. But let's see now an example that is not going to give me any matrices. So this graph will have one loop. So I have one V and one E looking like that. So think about what your paths are here. So I have V, I have E, I have E, I have E, and so on, right? And then if I add these ghost paths, I have E star, I have E star, E star, I have E star, E star, E star, and so on, right? So it's very, well, let's actually see the axioms too. So E star E is V, and V is regular, emits only one thing. So V, so this is Ck1, right? And Ck2, V emits only one thing, so there will be one term here. So that term is going to be E star. So that means that I can think of V somehow as some type of 1. And then that tells me that these 2 are inverse to each other. So if I'm thinking that E is some kind of some type of X, then E on N is kind of X on N, and E on E star would be X on -1, and E star N times is going to be kind of x on negative n. So if these are my algebra bases, then my linear combinations of these basis elements all look like something like this. So I may have a number and then x on a power, and then I may have another number, x on maybe negative power, right? And I have finite sum of those. So that algebra is denoted Kx inverse, and remember it will appear a lot in these subsequent talks. That's why I wanted to cover it today. So these are called Laurent polynomials. These are again finite polynomials, finite sums of linear combinations that each monomial has scalar multiple from k, right? Element from k, and then power of x on positive, negative integer, doesn't matter, right? So this example, with let's first put the negative power first. So 5x on negative 3 plus 3x2 would correspond in Leavitt path algebra to like 5 E star E star E star plus 3 E, right? So there is this isomorphism here. And I'm not sure if I want to hold you any longer because I'm already talking a lot today. Maybe let me just give you one final exercise and then we are done for today. So in this example here, we have seen that V corresponds to 1, right? And there was only one vertex, right? So that is kind of, you know, all the vertices are already listed here. This example here is more, in a way, general that it may appear. So in general, if E0 is finite, try to show that sum of vertices is 1. So I will just start you on that. Let that be our little homework for today. I will start you on that and then try to write down the details on your own. So an important hint for you to be able to go over this little homework is that every element of Leavitt path algebra LPA, that's short for Leavitt path algebra, is of the form finite sum of elements, coefficient is from the field, and then P, Q star are P and Q are paths. So K is in K, and P and Q are paths. And if you convince yourself of this, then I think that using the axiom, the axioms, you can show that sum of vertices is going to be identical. So let me just tell you why this is true. So what is our basis? Our basis so far are vertices, edges, and ghost edges. But remember that it's algebra, so we can multiply these basis elements. So that pretty much creates paths, right? If I multiply edges that are not ghosts, that creates good old paths. And if I multiply the edges that are ghosts, that creates elements of the form Q star. So why is it that always P comes before Q star? Why is it that first is real part and then is the ghost path? Because of CK1. So let's just give one last glance to CK1. So CK1 tells you that E star E is range of E and F star E is 0 if E is not equal to F. You see that axiom, using that axiom, you can push ghosts in the back. Because if ghost comes before non-ghost, that's how you get rid of it, right? So you see, that's why you will always be able to push ghost edges in the back. So this is how a typical element of your Leavitt path algebra looks like. And this is useful also because, you know, you want to be able to represent these things that you are working with, right? So, I mean, yes, so far we have seen some products and this and that, but in general, it is good to understand what your algebra consists of. Well, Leavitt algebra consists of these things, right? And this is true regardless of if E0 is finite or not. This is how your typical element of Leavitt algebra looks like. So, so if E0 happens to be finite, then the sum of vertices is 1. And I will also just leave you with one last comment, that if E0 is not finite, then finite sums of vertices are local units. What does that mean? What is a local unit? I think that we mentioned that yesterday. I think that we were talking about, yeah. There was a question yesterday, so we talked about local units yesterday. So let me just remind you what that means. So for every xy from Leavitt algebra, there is such a finite sum of vertices. Let's call such finite sum U, such that U behaves like identity for x and y. So xu is x, and u, and same for y, right? Maybe necessarily you don't have to convince yourself of that, but try to see why is it that that's going to work always. And then we can continue tomorrow.
Okay.
So are there any questions?
Yeah, so Leah William has a question on the chat. He's asking, Professor, can I relate the LPA with some groupoid algebra, maybe using a particular case of Ck2?
So these groupoid algebras, I think that's in the afternoon, right? So these are like more general than Leavitt algebras. I think that the speakers in the afternoon sessions are going to talk about that, or already did maybe.
Okay, so any more questions?
We had such a nice chat, I think, at the end of yesterday's talk. So if you want, just want to return to something, we can go over that in more details, so that will work.
Okay. Well, if not, let's thank Leah.
Okay. You don't have to give me applause every time. You will see me for 3 more days. So let's save that for the end.
Okay, thank you, Leah. See you tomorrow. Then.
See you tomorrow.
Double section. All right.
Bye.